Hey, so we decided to do our term project on Minecraft, and we specifically focus on an image database. So this is Nancy, and Nancy is currently a junior in college, and she's an electrical engineering major. She has her finals coming up, but instead of studying, she decides to play Minecraft to de-stress. But this is her first time ever playing Minecraft, and she realizes that she doesn't really recognize the ores. So instead of Googling it like any other person would, she decides to train an AI to recognize the ores for her. She's probably just doing this out of boredom, even though she should be studying, but she probably needs something for her cover letter because she needs an internship.
This is a way for us to try to understand it while also indulging in our interests. The ability of AIs being able to recognize images often helps improve efficiency and accuracy that manual recognition lacks while we're applying it to a game. This concept is important in other fields.
This concept is really used in more of like the medical field when they're using MRIs to scan and they're looking for tumors. One of the databases I found when I was scrolling through online is I found a database that was trained to recognize when people fell, and it was specifically geared towards the elderly. So when a security camera detected that an elderly person fell, they would call the correct services to come and help them. And another one is facial recognition. It's all around us now, and it's most likely already in your phone, maybe even your laptop or anything else. It wasn't really seen back then, but now it's just everywhere. And there's a bunch of databases online that are specifically geared to recognize people's face. And another one is there's a database online where they trained an AI to recognize weeds in gardens, which can be specifically helpful for people who have vision impairments. So we all need to start somewhere with our database. So we specifically went to RoboFlow, which is a platform with multiple databases and models that are meant specifically for computer vision. And that website often encourages their users to learn how to train and test with machine learning algorithms. Our specific database was published by user MindGuide in February 2025. So our data set has 8 attributes, which contributes of all the ores within the game. So we have diamond, coal, iron, lapis, redstone, emerald, gold, and copper. And we have a lot of images within this data set. There are 969 total images, and there's 678 in our training set, which is 70% of the set, 194 in the validation set, which makes up 20%, and 97 in the testing set, which makes up 10%. There are no missing attributes, and all the resolutions are 640 by 640. So what types of models and algorithms should we use? So we did decided to use YOLO, which stands for you only look once, K nearest neighbor, and K means clustering. We'll go more on onto why we decided to choose these algorithms later in the presentation. So we have our data set now, but it's not organized or convenient to use. So now we start the pre-processing. So one of the biggest issues that we had just throughout this project is we did not have enough RAM. Sometimes we would try to run a cell and it would immediately break because we went over our RAM limit. And we're college students, we're broke. We're not paying $10 a month just to run this. So we had to cut down our set. So instead of having all those 969 images, we decided to cut down each set to 20% of the original and we randomly chose these images. So instead, we have 135 images in training, 38 in validation, and 19 in testing, which is easier for us to work with. And we also changed the resolution because we realized that 640 by 640 was way too much for us to handle. So we ended up resizing the images for convenience to 128 times 128. And in this figure right here, you can see in the red box one of the ores that is in the bottom right corner. So we also tested different options of how we wanted to like scale and convert these images to something that was easier for us to use. So our first option was scaling and then converting. And then option two was just converting directly. And then three was clipping it and then converting it. You can clearly see which option we did not choose. We ended up deciding with option one because it was a bit easier to use, but option three probably would have been fine as well. So we also normalize our data using the max/min values. And using this method helps each pixel value be uniform while still maintaining the data relations. So that way it's smoother for us once we go into the training set. We also had annotations that came within our data set. So we had to connect those to our data set because there was usually an image ID that connected it. So like let's say one was coal and then the image URL will have something that said that one, it was a coal image. So now we pre-processed it and we can use it, but how can we use it? How can we get to know our set so that way we understand it later once we're doing training and testing? So we use 3 specific data explorations. We use PCA, which stands for principal component analysis. We use histograms and we use bounding box sizes.
So, PCA, basically, the most simplest way we can put this is think of a camera looking around at its scenery. You're trying to look at the best angle to take a picture, right? Well, in PCA, essentially focusing on clusters of pixels from our image data set. And as you can see here, many of our images did in fact cluster with one another. The clustering here is good because the closer the points are to one another, the more similar their image features are. Here on our axes, you can see principal component 1 and principal component 2. PC1 contains the direction of the greatest variance in our data, and PC2 has the next largest direction of variance orthogonal to PC1.
So now we're also moving on to our histograms, and histograms of pixel intensities can be very useful for understanding the distribution of colors and brightness in our images. And this can inform pre-processing steps like the contrast and the adjustments that we made. So it's crucial to ensure that your dataset's colors are distributed as expected. So we kind of use an analysis of marbles in a jar. Each marble represents a pixel, and each jar corresponds to a specific shade of red, green, or blue. Some jars overflow, meaning a particular intensity dominates the image, while others barely have any marbles, indicating scarcity of that tone. Kind of like on this figure, you can see that the blue is overflowing, but there's really isn't any red or green. So that you can see here in our histograms that our data is very clustered together, and we don't really want that. We want something that's a bit more spread out. So if our standard deviation and range are very small, less than zero point 0.1 for normalized data, then the histogram is within a narrow range, which you can see here in our images. It's all basically between zero point 0.1 and then to zero point 0.5. So our range for each of the color channels averages about to zero point 0.8, but each of the standard deviations for the histograms fall under less than the zero point 0.1 criteria. So because of this, we should increase the contrast of the images in the dataset to see if this number can improve. So since our data isn't spread out, how can we fix that?
So this is where a process known as CLAHE, otherwise known as contrast limited adaptive histogram equalization. So CLAHE is a way to make images look better by improving their contrast, as Elizabeth just said. Imagine dividing an image into a grid of smaller squares like tiles. CLAHE works on each tile individually to enhance its contrast. It does this by analyzing the brightness levels in the tile and then redistributing them to make the darkers darker and the lights lighter. However, to avoid making the image look unnatural or noisy, CLAHE has a special feature called a clip limit. This limit prevents extreme changes in brightness, so the contrast enhancement remains smooth and balanced. After adjusting each tile, CLAHE blends the edges of the tiles together to create a seamless transition across the image. The whole process helps to reveal hidden details, improves the visibility of important features, and makes the overall image more appealing to the eye. In our case, CLAHE can be on our MineCraft ore image dataset to emphasize the colors of the ore in contrast to the darker cave environment. A traditional histogram equalization is like cranking up the brightness of all the lights at once, making everything look evenly lit but potentially washing out important details. CLAHE, on the other hand, is like individually adjusting each spotlight based on the section of the stage it illuminates. If one area is too dark, its local spotlight gets a boost, while areas that are already bright don't get overexposed. Additionally, CLAHE prevents certain lights from becoming too intense, ensuring a balanced look across the entire scene as visually represented on these graphs. So when comparing these histograms to our previous histograms, you can notice that there isn't much clustering as there was before. In fact, the clustering even shifted it a bit more. So it is now mostly concentrated on the ends of our interval from 0 to 1, 0 to 1 being darkest to lightest, the extremes of our range.
So then finally, we use bounding boxes sizes. And the reason I put X marks the spot is because it's basically a map. So what bounding boxes specifically does is that it just highlights what you're looking for in your image. And in our case, that's the or. So it's often represented in a coordinate such as X, then Y, then the width, and then the height, which is mainly common in the Cocoa JSON format, which is what we use to download our data file. So there are different sizes of bounding boxes depending on the situation. And in this one, you can kind of see more of a wider, taller, larger bounding box because of the way the iron ore is shaped in the image. So usually for larger bounding boxes, you're encompassing more of an object. And then for smaller, it covers more finer details, such as minor ores that might be all the way in the back rather than on the front. So bounding box sizes must be proportional to object scale to ensure that the model correctly detects Minecraft ores in different image resolution. That's not really more of an issue for us since our resolutions are the same and we wanted to keep it evenly distributed. So now we can train. So we decided to start off with K nearest neighbor because we wanted to start with a model that was simple and then move our way up towards the harder ones. KNN can be applied to image data sets, by comparing the pixel or feature similarities between images. And unlike deep learning models, KNN does not train a complex model. It finds the closest matching items based on mathematical distance. So the way it works with images is that it has to convert the image into a feature vector since we cannot put images directly into a KNN. So they must be transformed into numerical representations. And these features can include raw pixels, the histograms, textures, or deep learning embeddings. And then we have to choose a K value. We chose a K value of 100 just because of the size of our data set, but a smaller K might ensure accuracy, but also might be sensitive to noise, and a larger K sometimes will average better results. So Canon identifies the K most similar images and assigns a label based on the majority voting. So with our MineCraft ors, it'll follow this step process and then it'll compare the image to an existing labeled or and then assign the label to the image based on the closest matches. So when we did our validation for this set, we did 5 folds and we ended up with an inaccuracy of 18%. And that's a change from our original, which was 20%. So with this validation, it went down. Either way, it's not a very good accuracy, but this was expected since KNN isn't really meant for complex images as a data set, since sometimes the images can be far away, they can be closer, the lighting could be different. It's not really meant to handle something like that. It's more of something simpler, like let's say there's stone and grass in the game. You probably could have used it more often for that if your images were right in the center. So this is when we kind of really noticed that our error for a KNN with this data set really wasn't good. Our highest was about 0.93.5%, and that's at a K nearest neighbor of about 19, 18. Our lowest was around 86.5%, and that's still not good either, but it was something expected.
So the next method we chose to oh no, hold on. The next method we chose to go into was k-means clustering. It sounds very similar, but it's actually quite different. So k-means clustering is an unsupervised learning algorithm that helps analyze and group images based on similar features like color, texture, or patterns. Um, it is also a very efficient method, which was very useful for us considering we were consistently running out of memory. Um, so on the graph, no. Visually, you can notice the clustering happen as it happens. So we circled an area which we deemed to be the most clustered. This area also happens to be around 0. Um, it is a very good thing that it is around 0, as fuck, why was it good again? Keep
It's
forgetting
good,
it.
but it's good.
I might just cut that out.
Yeah, I think you might have to. Um, the way it's clustering. Uh, hold it, hold it.
Um,
Uh,
okay, let me move on. So visually, you can notice the clustering as it happens. We circled an area which we deemed to be the most clustered. Um, Moving on to our test. No, fuck. Why is it moving forward? Moving on to our testing set, you can also notice a pattern between the two. So they both happen to cluster around the same region, which is quite good for us because that means that we, in fact, did the method correctly. And you may also notice that there are many, there are much less points than there were in the previous set. This is because our training set is, what, 100 times bigger than our testing set. So that's bound to happen. Um, and then these are some of our numbers that we got when validating this through this method. So the silhouette score is a metric used to evaluate the quality of clusters, particularly in k-means clustering, by measuring how well data points are clustered within their assigned groups compared to other groups. This ranges from -1 to 1, the higher the better. Although 0 is the perfect middle ground between this range. As you can see here, we attained a value of 0.08. Similarly, our bootstrapping score was also close to zero. This is important to note it, as it moves closer to one, it runs the risk of overfitting, which would not be ideal when analyzing data sets. Another method that we used is YOLO, um, also referred to as you only look once. YOLO is a powerful deep learning based object detection algorithm that processes an entire image in a single forward pass, making it extremely fast compared to traditional method. These are the values we attained the one time YOLO was successful. Um, so these values are the mean average precision, also known as MAP, precision, and recall. MAP evaluates overall detection accuracy, while precision measures the accuracy of positive predictions. It tells you how many of the objects that the model detected were actually correct, basically identifying true positives. While recall measures how well the model identifies all actual instances of an object, it tells you the proportion of actual objects that were correctly detected. In summary, images were normalized and reshaped to ensure uniformity and computational efficiency, mostly due to our RAM problems. PCA and clustering techniques revealed underlying trends and potential relationships within the image data. Histogram analysis identified low contrast in original images, prompting the implementation of contrast-limited adaptive histogram equalization, also known as CLAHE, which I struggle to pronounce, to enhance OR features, binary masks, and color space. Oh no, we didn't do that anymore. Okay, cut that out. And then models such as, oh, I didn't, oh, is this outdated?
Yeah, that's really outdated. We didn't use like we only use K-means out of all those.
Then
That's the end of our project. We're sorry we turned this in late, but we had a lot of difficulties regarding the RAM, and it really made us realize that how hardware intensive machine learning can be, especially with images. It was like every 10 minutes it crashed, or that we didn't have enough RAM, the memory ran out. It was a lot of things, but